Alright, in this section we are going to look at how polynomials, zeros, and factors are all related. So we've already been talking about zeros some, and we know that real zeros we can see as x-intercepts from the function, so that doesn't change here. And we definitely could find the zeros of this function using the graph. However, we also want to look at how to find these algebraically. So if we have a function that is already factored out here for us, so we see things that are multiplied in parentheses here, it makes it pretty easy to find the zeros of this function. Because if I look at what values I could plug in that would make this 0, if I make any piece of this function equal to 0, any factor of this function equal to 0, then the whole thing will equal 0. For example, one of the zeros of this function is 4. So if I plug in 4, I would have 5 times 4 squared times 4 minus 4 times 4 plus 2 times 3 times 4 minus 5. Well, I know that this is going to equal 0 because of this factor right here. So it really doesn't matter what happens with these other numbers. It's going to be 5 times 16. Right here, 4 minus 4 equals 0. So I'm multiplying everything by 0. So it doesn't even really matter that this is 6 or that down here we'd get 12 minus 5 would give us 7. Because if I multiply anything by 0, I will get 0. So, anything that would make any factor 0 is going to be a 0 of this function. So x equals 4, we just said, is a 0. That comes from this factor right here. We would also have anything that would make x plus 2 0. Well, if I plugged in a negative 2 here, then that would be a 0. For this part of the function, if I plugged in a 0, 5 times 0 squared, that would equal 0. So x equals 0 is a 0 of the function. This last part is kind of the trickier one because it just doesn't jump out at you quite so quickly. It's not positive 5 because 3 times positive 5 would be 15. Minus 5 would give us 10. That does not equal 0. So if you're having trouble seeing what value it would be, what you can do is you can just take that piece of the function, that factor, 3x minus 5, and you can set it equal to 0. And then you've just got a little equation here to solve. You can solve it by adding 5 to both sides, and then 3x will equal 5, and then you would want to divide by 3 to get that x by itself. So x equals 5/3 would be a 0 of that function there as well. And one other quick note right here, because this x squared has a square with it, then that means that the multiplicity of this 0 would be 2. It would count twice there whenever you're talking about the real zeros of this function. So what we're going to see is that we have a factor such as x minus a is some sort of number here, then a ends up being a 0 of that function. So when we see a factor where we have x minus 4, then positive 4 ends up being a 0 of that function. So let's look at the graph of this real quick, and just remember that we can see this from the graph as well. So I've already graphed this function here. This is the function that we're given in this problem, and you can see right there at -2, 0, 1.6667, which is 5 divided by 3, and 4 are all going to be zeros for our functions. That's what we have. You can also see that at 0, we have a bounce on that function, so that is going to be a multiplicity of 2. That 0 is going to count twice there. So let's move on to our next one. Again, you can find these from the graph, so whenever you're asked for the zeros, you could just graph this But it's really simple to find the zeros by hand for these as well, because you are just looking for anything that would make any of these three factors 0. So you could say 3x minus 2 equals 0. Well, to solve that, you just add 2 to both sides. 3x would equal 2. And then you could divide by that 3. So x equals 2/3 is one of the zeros. Then you could take the next factor. You probably can do this in your head. You probably don't have to write it out. But what you're doing is x plus 7 equals 0. So if you subtract 7 from both sides, it just switches the sign. You get x equals -7. And you can probably already see that the last one's going to be x equals +4. It's just the opposite sign. As long as there's not a number in front of your x, that's all that happens. But what you're doing is you're thinking x minus 4 equals 0. So you add the 4 to both sides, and x will equal 4. Now, you don't have to do it this way. You can look at the graph instead, but honestly, it's much faster if it's already factored just to do this for each one. So if we look at the graph for this one, here I've already got it typed in for us here. There's our function, and you can see we got x-intercepts at -7, 0.6 repeating, which is 2/3, and 4. Those are our 3 x-intercepts, so those are our 3 zeros for this function. So if we look at example 2, we're asked to find all of the x-intercepts. So again, we're just going to say that this factor equals 0, so 3x equals 0. Here I would just divide by 3, and so x would equal 0. If you ever have sort of like a greatest common factor pulled out like this, you're just going to get 0 as a function here. You probably do this part in your head. You got x minus 2, so it's going to become +2 as your 0. Right here you've got x plus 3, so that's going to be x equals -3. This little square right here tells you that you have a multiplicity of 2 right here. That 0 counts twice because you have that square. And then the last one you probably want to set up a little equation for. You got 2x minus 3 equals 0. So you just have to add 3 to move that 3 over to the other side. 2x would equal 3. And then you'll divide by 2. And so x equals 3/2, or if you want to do 1.5, that's fine as well. So you've got these 4 distinct zeros. It really counts as 5 zeros because that -3 has a multiplicity of 2. Again, you can graph it. Perfectly fine just to graph it instead. Here it is typed in for you. You can see you've got zeros at -3, 0, 1.5, and 2. Those are the zeros we listed. And notice right here at -3 that one is a bounce, so it counts twice for that. So when these are already factored for us, they're really pretty simple to solve. Now we will run into a few things that are going to be a little bit more difficult. And one of those things is going to require us to use the quadratic formula. So in Math 2, you do a lot of quadratic formula. And with the quadratic formula here, whenever we have a quadratic equation, we'll have ax squared plus bx plus c equals 0. And to solve that for our x, we can use our formula here, -b plus or minus square root b squared minus 4ac all over 2a. So for this, you just need to find your a, b, and c. In order to do this, everything has to be on one side, which it already is here. In front of my x squared, I don't have a number, so I'm going to put a 1 right there. So my a value is going to be 1. My b value is going to be the number in front of my x, which is -5. And my c value is going to be -8. So if I want to solve this here, I could say that x is going to equal -b, which is -5 here, or some people will say the opposite of b, so it changes signs there because negative becomes positive, plus or minus square root, b squared, make sure you put parentheses around this right here or it will not give you the correct answer, minus 4 times a, which is 1, times c, which is negative 8, all over 2 times a, which is 1. Now, you could type this into the calculator, you'll get a decimal, that's fine. But a lot of times they don't give the answers as decimals. They give them in the exact form. So it will look more like this. So negative 5 is really just positive 5, plus or minus. And then this negative 5 squared minus 4 times 1 times negative 8. We could use Desmos for that. So for that, we would be doing negative 5. Make sure you've got parentheses there. Minus 4 times 1 times negative 8. That's going to give us 57. So we've got 5 plus or minus the square root of 57 all over 2. Sometimes that root right there will break down. I don't believe it does for this problem. So they'll usually leave the answer like this. Now, if you want a decimal answer, for this, you would just go over here and type in 5 plus the square root of 57, all divided by 2. There's one of your answers. And then I'm just going to copy and paste this and change that plus to a minus. And there's your other answer if you're wanting a decimal. You also can do these from a graph as well. And we'll see that on the next problem. So that's just a little review on quadratic formula, because sometimes you get problems like this and they ask you for the x-intercepts. So if they ask us for the x-intercepts here, the first thing I would want to check is to make sure that this won't just factor further, x squared minus 4x minus 10. So I could try to, do x method for this, so multiply to get negative 10, add to get negative 4. But my only options for negative 10 would be 2 and 5, negative 2 and negative 5. Or, I guess positive 5 there. Or negative 1 and positive 10, or I could switch those signs. None of those are going to give me negative 4. So this does not factor here. So what we would do is we would say that 2x minus 3 needs to be 0. This one's a simple one to solve, so I just add 3. 2x will equal 3, and I'll divide by 2. So x will equal 3 halves. That'll be one of our zeros. And then over here, I would have to use quadratic formula because I'm going to have x squared minus 4x minus 10 equals 0. So I would say x equals the opposite of b. Since that's a negative 4, I'm going to make it a positive 4. Plus or minus square root b squared, so negative 4 squared, minus 4ac, so 4 times my a right here is 1. My c is negative 10, all over 2 times a is just 1 there. So I get 4 plus or minus, this is going to be 16 plus 40, so square root of 56, all divided by 2 right there. I believe that will simplify and break down a little bit, but since I'm not there today, we're just going to stick with this right here. It'll be good enough. We'll work on how to simplify those later. It's important to note that these are still real zeros. So 4 plus or minus the square root of 56 over 2 is still a real number because it doesn't have an I. If I go over here and type it into Desmos, if I do 4 plus square root of 56 all divided by 2, I get a real number. Or if I do it with the minus sign, I also get a real number. So these are still real zeros. You can graph and find these as well. So right here I have that function graphed here, I believe. Oh no, it's, yeah, right there. And so if I click right here, you can see I've got negative 1.741, I've got 1.5, and I've got 5.741. These are the decimals that go with that exact value there, and then 1.5 is 3/2 for that. So you can still use the graph. It's just going to give you the decimal version, whereas if it's multiple choice, that decimal may not be what they're looking for. Okay, so let's keep moving on a little bit. We need to do just a little bit of review of simplifying square roots here, because we may see that on some of the problems that we run into. So for example 4, this should be a very simple one for us. When we see square root of 25, it is asking us what number times itself gives us 25, and the answer to that is 5. 5 times 5 equals 25. So that is a perfect square, is what we call those. So that breaks down really nicely. However, square root of 32 is not a perfect square. So there is not a number that we could just say that number times itself equals 32. We could get a decimal if we typed it into the calculator, but that won't work when we get these negatives here for 6 and 7. So we need to do something different here. So whenever I'm thinking of 32, if I think of those perfect squares, I could, like a number times itself, 2 times 2 would give me 4. So 4 is a perfect square. 3 times 3 would give me 9. So 9 is a perfect square. 4 times 4 is 16. 5 times 5 is 25. And that keeps going. These are all perfect squares. So what I can do here is 32 is actually the same as the square root of 16 times the square root of 2. Because 16 times 2 gives you 32. So if I break it up this way, I can take the square root of 16, which is 4, and I cannot take the square root of 2, so it would stay underneath the square root. So we would simplify the root like that. This is something that you do in Math 2 as well. You use it some whenever you're looking at quadratic formula. I know Hunter just did this pretty recently with Miss Swisher in his Math 2 class. So what happens whenever we have negatives under the square root? This is where the I is going to show up. Because if I look right here, 16 is a perfect square. I can take the square root of 16. But 16 is also being multiplied by the square root of -1 because I have a negative here. So when you have a negative, you're going to get an I. In this particular case, there won't be a root left because the square root of 16 is 4 and the square root of -1 is I. So I would just have 4I. For that, we're going to see this some whenever we have imaginary roots that we have to find. If we look over at 7, 150 is not a perfect square, but 150 could be written as 25 times 6. So what I could do is I could say this is the square root of 25 times the square root of 6 times the square root of -1. So the square root of 25 is 5. The square root of 6 we cannot simplify, so we would leave it here. And the square root of -1 is I. Now, typically this will be written this way instead, 5I root 6. Okay. Now, we won't have to deal with this very much. The main thing that we're going to have to see this for is whenever we are finding roots that are imaginary, because we can't find roots that are imaginary from the graph. So let's look at an example of what we're going to run into here. Here we see f of x equals 2x minus 1 times x minus 5 times x squared plus 25. So for this, we would want to be finding all of the zeros for this. So I would be thinking 2x minus 1 equals 0. And this is just a regular root. You would add the 1. You get 2x equals 1. You would divide by 2. And so x equals 1/2 would be a 0. I would also have x minus 5 equals 0. This one's simple enough we can just do it in our head. We'd get x equals positive 5. Okay, those are our two normal zeros. But x squared plus 25 is going to have something kind of strange happen. Because we're going to say x squared plus 25 equals 0. And To solve that, I would need to move the 25 over to the other side. So I would subtract 25. And so I will have x squared equals negative 25. Now, to get rid of a square, I would need to square root both sides. And so when I square root both sides, I would get an x over here. But I've got the square root of negative 25. What that's going to give me is 5 with a I behind it, because that's going to be the square root of 25 times the square root of negative 1. Now, you may also recall that when we were talking about imaginary roots, we said they always have to come in pairs. So I can't have just these three answers, because that imaginary root has to have a pair with it. So when we square root both sides of an equation, we have to put a plus or a minus right here with it, meaning that x equals positive 5i would be a 0, but x equals negative 5i would also be a 0. So that's going to happen every time that we have an imaginary root. We'll have the positive and the negative of that imaginary root. Now, if we want to look at this one on the graph, we do have to be able to do some of this by hand, because over here I have already graphed that function. So let me pull that up. It's this one right here. And if we look, we have zeros here at 0.5 and at 5, which were the two real zeros that we found. But even if you zoom out, there's no other roots for that function. And that is because those roots are imaginary and they can only be found by doing this by hand. So that's why it's important for us to know both ways here. So, going back here, example 9 is going to be our most difficult problem because number 9 is not factored for us. So since 9 is not factored, we are going to have to factor that by hand and use long division to do so. However, our graph can help us some here because we can find real zeros with our graph. So if I look at the graph for that one, I have it already typed in here. So the graph of 2x to the third minus 4x squared plus 16x minus 32 just looks like this. And if you zoom out, you can't find another 0. It's just got a single 0 right here at 2. So using what we know about zeros, if x equals 2 is our 0, which is going to be one of our zeros, then x minus 2 would be a factor. So what we're going to have to do here is we're going to have to do some long division. Thankfully, it's a pretty simple long division. We're going to have to divide 2x to the third minus 4x squared plus 16x minus 32. We're going to have to divide it by the factor that would go with x equals 2, which is x minus 2. Notice the sign changed there. And then we're going to do our long division. So I'm going to say, what times x would give me 2x to the third? And so that is going to be 2x squared. And so I'm thinking 2x squared times x will give me 2x to the third. I must also distribute this here. 2x squared times negative 2 gives me negative 4x squared. I will subtract this here, which actually is going to cancel both of those out. And then I want to bring down my 16x. You really just want to go ahead and bring down that minus 32 as well. So next you're going to have to ask yourself, what times x would give me 16x? And that is going to be a positive 16. So 16 times x is 16x. And then 16 times negative 2 is negative 32. And so you'll subtract both of those. And they both cancel, so you get a remainder of 0, letting you know this is a factor. So what this means is that your equation really could be factored like this. X minus 2 times 2x squared plus 16. And we already found right here, this is x equals 2 is our 0 that goes with that first factor. For the 2x plus 16, or 2x squared plus 16, we would do this. 2x squared plus 16 would equal 0. We would subtract that 16 to move it over to the other side. So 2x squared equals negative 16. We would divide by 2, like that. So x squared is going to equal negative 8. And then we would square root both sides. And when we square root both sides, we will get x equals, we want to put a plus or minus here, and we're getting the square root of negative 8. We could break that down. We could break it into square root of 4 times square root of 2 times square root of negative 1. And I'm running out of room here. But the square root of 4 is 2. The square root of that negative 1 is I. And then you have the other square root that stays underneath the square root, and you would put a plus or minus with that. So those would be your two imaginary roots. And you can see here that we've got 3 roots. We've got x equals 2, and then we've got x equals positive 2i root 2 and negative 2i root 2. So that would be in line with our fundamental theorem of algebra, which tells us we're going to have 3 roots. This is the only one that you're going to have to use long division for. Most of the other types of problems you would be able to do either by using Desmos or by just setting the factors equal to 0 like we've done here. Our last question is going to ask us to match a graph. It is definitely an option just to graph this and see which one matches best. But if you're trying to do it in the quickest way, you could just find the zeros. So this is going to be x equals 3 right here for the 0. So you should have a 0 at 3. This one does, and this one does. But for B, A, and B, that one is a bounce right there. And this does not have a square with it. So it just has a multiplicity of 1. So that right there alone lets me know C should be my answer. I also, though, could go on to see that I've got x should equal negative 1 right here from that middle factor. So, like, I can see I've got a 0 at negative 1, a 0 at negative 1, and a 0 at negative 1. It is supposed to be a bounce. This one is for A, but 3 was already wrong. For B, this is not a bounce right here, so that's not going to be our answer. And then for C, we can see that we do have a bounce, so that's the one that has all that we need. X squared plus 4 is going to give us imaginary zeros, and those don't show up on the graph. You also, of course, can always just type this into Desmos. I already have it typed in here, and you can just kind of see what's happening on that graph. Right there I got negative 1. Right here I got 3. At that negative 1 it's a bounce. Zooming in or out to get it matched the graph might be difficult, but if you just check those zeros you can get those to match up. So that is all we're going to do with linking the zeros to the factors that we have. You are going to have an assignment on Amplify. So if you go to Amplify there, let me pull this up right here real quick. Okay, so looking at this assignment, it has several different things that you'll work through. It'll ask you things like what are the zeros. You'll check the ones that are correct. There's several questions like that. This asks you specifically what types of zeros that a function has. So, you'll have a few matching where you have to match the function to the graph there, and then the next slide will check it for you to see if those are correct. Here is another multiple choice question. This one you're going to have to write your own equation for. Another matching, and then one more where you write your own function. So this is your assignment. It will be due tomorrow, and then we'll go over it. We'll also take our quiz for 3.1 through 3.3 on or tomorrow on Tuesday, because I didn't want you to take it today without me being there to go over